So I'm Angela Gurnell, as you can see, and I work in the University of London. Queen Mary is one of the colleges of the University of London. And I'm going to talk about the hydromorphological framework that we've developed within Reform. And I'd just like to say at the outset, this is literally a framework. So it's not a series of calculations that you need to apply. It's not a cookbook. It's a way of thinking about rivers which encourages those who are managing rivers to look beyond the reach to the context of that reach and how that context changes through time as well as you change the spatial scale. So it's a very open-ended framework, and we designed it bearing in mind that different member states of the European Union have their own ways of doing things. They have their own survey methods, their own data sets and so on. So this is a framework to encourage member states to, if you like, organise their data in a certain way and think about it in a certain way, and indeed modify the framework if they feel it is appropriate, but at least to look at this larger spatial and temporal scale for assessing and managing rivers. Okay, so these are the topics I'm going to talk about. I should say I can only skim over the surface. Life is very complicated in this area. The last slide gives you reference to the major deliverable that deals with this within Reform, which you can download from the website. But there's also a special issue of Aquatic Sciences, the journal Aquatic Sciences, in progress, which will actually be far more accessible to look at, I think, than our extremely large report. But they're both listed on the last slide. Okay, so I'm going to talk through, first of all, why we developed this framework, what its aims are, then go briefly through the stages so that you can at least see how the stages fit together, even if you don't appreciate the detail, and then run very quickly through an example at the end to show you how this framework can actually work quite successfully. Right, so first of all, the aims. So the aim is to provide a means of developing a broad space time understanding, if you like, of how a river reach might work within the context of its catchment and the region of Europe in which it's located. So by taking that approach, hopefully we understand in reasonable depth why particular reaches are the way they are, how stable they are, and indeed how they might change in the future as controlling conditions change. And of course there's going to be one set of conditions that's, in my view, definitely going to change in the future, and that's climate. So we can at least start to appreciate how our rivers might adjust to scenarios of climate change, but also to other scenarios as well that are more local. So that when we're looking to intervene in a particular reach, we do it in a way that is as sustainable as possible in the context of processes, whilst of course taking account of all the things that Ian's just been talking about, the sort of human constraints. Okay, so the way this analysis goes is that first of all, we look at our reach or reaches that we're interested in, and we delineate those reaches and the units of space that they're located in, up to the catchment and even beyond, so that we understand where we are in the spatial arrangement of the landscape. So we delineate these spatial units, and I'll talk more about that in a minute, and then we proceed to assemble the information we have on those spatial units, which is what we call characterising. So what information have we got, and there's guidance as to the sort of information you need, but the precise information is likely to vary from member state to member state. And if a member state doesn't have that information, we make some recommendations for the sort of pan-European data sets that are available that you can draw on, of which there are an amazing number. From that characterisation, then we extract indicators of processes that are going on, or of human interventions and impacts which are working with or against those processes. So we go from a broad characterisation to indicators, and then those indicators allow us to assess certain properties of the reach itself and of the larger catchment within which it sits. And on that basis, we develop understanding of how the catchment and the reach are adjusting through time to different processes and different interventions. And on the basis of that understanding, we're then able to consider what might happen in the future if certain scenarios of change occur, of which, as I say, the obvious one is climate change. Okay, so if we work our way through these, and I apologise, this is going to be a very brief, high-level overview. But we start by, at our reach, that is the key scale. That's the scale at which we go and mess around with rivers on the whole. So we start with the reach, but we have a look at these spatial units within which it's located or are upstream of it and are therefore likely to affect it. And we delineate these, so we know what biogeographical region we're in, but that clearly defines the climate. It also defines the potential vegetation. And the one thing, you know, I will emphasise again and again through this presentation is we mustn't ignore vegetation. It is so important. And in a way we're not helped within the Water Framework Directive because the biological quality elements are all focused on the channel. We do not assess beyond the channel. But in fact, the riparian system is absolutely crucial to dictating the potential of our channel. So within our framework, we look beyond the channel and we look at vegetation. So we define our catchment by the watershed. We all know how to do that. But we then look within the catchment. Are there broad sort of landscape types there? For example, typically you might have mountain headwaters, then sort of foothill areas, then maybe a plain. So you've got three quite clear landscape units there, and they're going to function quite differently. So we define our landscape units on the basis of topography, geology, and land use, or land cover, because that will reflect these other processes and conditions. We then look within the landscape units at the river network, and we define segments of that river network, which might be anything from 10 kilometres upwards. But they're chunks of river where you get major changes at either end, maybe because there's a large tributary junction. That would delimit the end of a segment in many cases because you've got a big change in catchment area. There may be a change in slope simply because of the underlying geology and topography or the glacial history or whatever. So we define these segments, and then within the segments we define reaches. And reaches are defined on two grounds. One is, if you look at them from the air, they look similar. So the river pattern is sort of similar. But also, it gives you a way of looking at major longitudinal discontinuities like in-channel structures, which often define the units you deal with in the Water Framework Directive. So it means that you can map your reaches and segments onto the water bodies that we have to deal with when we manage our rivers within Europe. Okay, so we define these. If you're just interested in one reach, then you only have to define that one reach and the segment it's in and so on. If you're interested in integrated catchment management, then you could, you know, split your whole river network up into pieces like this and use it in the long term for managing your data and understanding what's going on. Okay, we then characterise these spatial units. And as I said, the reach is the key unit. And one of the things that is absolutely central to our method is allocating our reach to a river type. Now, that doesn't mean to say that we believe that rivers can be chopped up into types. They can't. There's a continuum. But nevertheless, there are broad types we can define. And once we've defined a type, we can then look at whether it's functioning naturally or not. So it's quite a useful way of approaching this. So we have a series of river types. We then characterise those reaches in terms of the smaller units within them, the features that are there, things like pools, riffles, terraces and so on. We look beyond the river to the whole floodplain and we pull together this information within the reach. We also look at larger spatial units than the reach, and there what we're trying to characterise is how those larger spatial units are delivering water and sediment to our reach. Because the hydromorphology is largely a function of river flows, sediment supply and sediment size, although vegetation is also important. So we try and look at that. We also, as far as is possible, look for evidence of what's gone on in the past. Because if you've had, for example, in Europe, massive, well certainly in the UK, massive land use changes during the Second World War, where we went over from pasture to cultivation simply because we needed food. And that change in land cover, of course, changed the amount of sediment getting into the rivers, and in our low gradient rivers, that sediment is still working its way through the system. So to interpret a river reach now, we need to understand that there was this massive input of sediment in the 1940s and early 50s. So we need to look to the past. And again, to try and look at flow and sediment in the past and how that may have affected our reach, and also now. Because that gives us the understanding to think about, if we start messing around with flow and sediment supply now, what's the likely consequences for our reach in the future? Okay, so if we look at some of these indicators, so this is a very brief overview, but it's the sort of logic that I want to illustrate. So here we've got catchment, landscape unit, river segment, and the key processes that we're trying to characterise by indicators. So it's very much from from the catchment right down to the river segment level. It's how much water and how much sediment of different size is getting into our river system, and how is the river system, if you like, interacting either in an artificial or a natural way with that water and sediment. So at the river segment scale, for example, we've got disruption of longitudinal continuity there. So have we got major structures in our river which is messing up this flow of water and sediment? At the landscape unit scale, we're looking at permeability, the degree to which runoff runs off quickly or is delayed, and the amount of sediment it's likely to take with it by looking at sediment sources and likely sediment production. And you can do this in a very sophisticated way if you want, but there are quite simple ways of doing this, which we recommend as a minimum. More interesting is the reach scale, because here we start to see the consequences of this. So what we try to do at the reach scale is to think about the energy of the river in that reach, the stream power, the degree to which the river can access its floodplain or not, and then starting with the river type, we start to look at the evidence for whether that river is functioning naturally or not, given its type. And we look at the channel, both the contemporary and historical evidence of changes, whether the features in the channel match the type we've got, the type we think we've got, whether the floodplain seems to suggest that we've got the right river type or not. And we also look at vegetation dynamics, the degree to which we've got a riparian corridor that is functioning, that exists and is functioning. Okay, so we can then move on, having assembled this information, having extracted indicators, to group those indicators together to make some assessments. So starting at the reach scale, the first thing we do is we look at our river type, and I'll spend a little time on this because it's quite important. But we want to know what type we've got. We have 22 types plus a zero type, and the zero type we deem artificial. And the only means of a type being artificial is that the bed is artificial. You know, you've got a concrete line channel, that's artificial. Otherwise, we start from the assumption that we've got something we could define in a natural context. So we look at our reach and we say, how confined is it by its valley? How many flowing channels has it got? What's their sinuosity? And what sort of bed sediment size have we got? So all of those, apart from the bed sediment size, you can clearly extract from a map or an air photo. It's very easy to run through and allocate these river types. If you have any sort of habitat survey in your country, it will record something about the bed material. So in the UK, we've got the River Habitat Survey, and it says whether you've got cobbles or boulders or sand or whatever. So there's existing information to define all of these river types. We also look at historical information, old maps, air photos, any old topographic surveys if you're lucky enough to have them, and consider whether the type has changed in the past, and whether there's any evidence that even if the type hasn't changed, that the river's been moving about. It might be getting wider, it might be getting narrower, it might be migrating. This is the first hint of dynamics. Okay, so we do that at the reach scale. To just talk about river types, if we have naturally functioning rivers, and there are some in Europe, not many, but there are some, there's an enormous number of types that you can get. So here's some pictures of some naturally functioning rivers, and they're arranged from top left, you go left to right along the bottom row, and you can see what you get as the balance between flow and sediment dynamics and vegetation changes. So at the top left, we've got this river in Poland, the Narew River, which is an anastomosing river. It's very, very low energy. It's got peat banks. In other words, it's got banks created by vegetation. It's got bars which are driven by aquatic macrophytes. It's vegetation dominated. And then as you go across, we go through very stable meanders to dynamic meanders to a transitional sort of wandering system here through island braided to a true braided system. And by the time you get to that braided system, the vegetation is irrelevant. It's all to do with water and sediment dynamics and very high energy system. So these are the sorts of systems that one can have, even naturally, before we start messing about with them. So we've defined these 22 types plus type 0. And the 22 types fall into two broad groups. On the left, we've got confined river types. So these are the river types you might see where they can't move very much laterally because they're confined within a narrow valley. On the right, we've got types you may well see within a confined valley, but often it'll be partly confined or unconfined. So these are more widespread types that you may see. And if you look at the right-hand box there, as you go down the left-hand side, we've got different broad sizes of bed sediment. And going across the top, we've got different numbers of threads and different sinuosities, basically. So we go from high energy multi-thread through transitional to single thread to low energy multi-thread channels as you drop the energy. So as I've said, rivers follow a continuum. However, you can allocate any reach to a type, and if you're not sure, just pick the nearest because you're not going to be far out. And then the aim is to have a look at that and have a look at all the other types that you've got within your landscape unit to see what the options are, because some reaches will be more heavily impacted than others. So rather than having some sort of imaginary reference condition which relates to humans not being there, what we try to do is to look at the river types you've got under current constraints and see what you might aim for, what's functioning best. Okay, so we then go sub-reach scale and we say, right, we've got this river type. Are the features that we see there appropriate given the river type? And we look at the features in the channel, on the margins and out on the floodplain. So again, if you have something like a river habitat survey, you've got a good starting point for that. You've got air photos to look for the floodplain features. So this can all be done as a desk study, provided you've got past field work in a river habitat survey to give you some indication of things you can't see from above. The other thing you have a look at with those present features is the degree to which they're telling you that there may be some issues here. So are the features missing that you would expect to see? Are the features that are degraded? For example, there are not as many of them as you would anticipate. Do the floodplain features suggest that that floodplain was built by the current river type, or has there been some sort of change? Because again, then you've got to ask why. Okay, and this is, again, we don't need to look at the detail, but in our report and in the various papers, we give a lot of information on these river types to give you guidance about what you're looking at. So on the right here, there's a very modified or very brief description for our current purposes of what rivers of that type might look like. There's also information on how naturally stable they are, because if you've got a fundamentally stable river type that's functioning naturally and you need to do something to it, you can do that with confidence because it's stable, so it's unlikely to react badly. If you've got an unstable type, then you could induce all sorts of problems if you're not very careful. And then the whole list of features that you might expect to see associated with that type, which are abbreviated here. So MCB, mid-channel bars, R, riffle, P, pool, and so on. And here are our 22 types, and we end up with the very stable ones at the bottom there. The other thing we tried to do is to go, as I say, outside of the river channel. So we've taken an existing floodplain classification that was developed many years ago, but it was what was called a genetic classification of floodplains. In other words, it classifies the floodplains that are developed from certain types of river. So we can list our river types down the left-hand side there, all the numbers, and we can associate them if they are building these floodplains with the type of floodplain they might be associated. And then on the right, we've got a sort of range of stream power in which you would expect to see rivers of that type and floodplains of that type. So it's not a cookbook, but it's guiding you to thinking, does this look right or doesn't it? And lovely pictures from the original article of what these floodplains look like, their sedimentary structure. Now, I know in Europe, our floodplains are often very highly modified, but there are usually hints there of these features that might indicate what the river was like that constructed the floodplain. Okay, also at this reach and within reach scale, we then start to do some assessments. So we not only look at our channel type and its dimensions and its stream power and all the rest of it, but we start to assess how it's functioning hydromorphologically. Does it look as though this river is doing the right thing given the type it is? Also, to what extent is it showing artificiality and interference by humans, and what are those interferences within the reach? We also look at the riparian corridor. Is there one? And if there is one, is it showing signs that it's functioning, that we're getting turnover, that there's interaction with the river? Or is it just a sort of pretty gardening feature along the edge of the river? And when we also look at hydromorphological adjustment, so are there features there and combinations of features which tell us that at the moment this river is changing? And if so, how is it changing? Is it incising its bed? Is it getting it wider? Is it silting up? Is it migrating? And then we've got our historical evidence as well, which is a longer term perspective on how that river is changing. Okay, we then move to assessments at larger scales. So here what we're trying to do is to look at current and past flows of water and sediment and whether they are appropriate to the river type we've got, or whether it's going to change anyway. because the processes have changed. So is our reach type appropriate for the current flow and sediment supply? Are there other types that exist within our landscape unit which are more appropriate to the flow and sediment regime? Because that might give us some hints about how we restore this reach if we're going to do so. And what are the changes in the broader catchment that have induced these changes in process? You know, is it just land cover change, or is it that somebody's constructed a dam upstream 20 years ago, or is it that we've messed about with the river itself extensively within the catchment, bank reinforcement and so on? So we start to try and link process change to controls that are beyond the reach as well as controls within the reach. And on that basis, we can then start to pick out the important changes and summarise them. So we can look at all sorts of possibilities, but this is an example that Massimo Rinaldi and his colleagues developed for the Magra River in Italy, where down the left-hand side, these are the key things that we identify through this method are having an impact at the reach scale. So at the catchment scale, it's afforestation. Within the broader river network, it's dam construction, bank protection, gravel mining. And within the particular reach, it's largely bank protection. So we can see how those changes have affected the processes at those different scales and how those processes have cascaded down, so that on the right, we've got indicators which pick up how these processes have changed and how their impacts have changed through time. So at the reach scale here, we observe changes in sinuosity, changes in river type, and so on. So it's a sort of space-time summary. You can also go to your particular reach, and we've got two reaches here, B and C, and look at broadly these key changes in their catchments, because each reach has a different catchment area, and their segment, and see broadly through time when those changes have occurred and how severe they have been. So that helps us to interpret for an individual reach rather than for a group of reaches. And then on the basis of that, we've really developed some good understanding. And I mean, if you're very sophisticated, you can do all sorts of modelling in here, but you don't need to. This can be a quite simple desk study to indicate where the issues are. And we then got to think, for any reach we're going to mess around with, how's it going to change anyway? Because we need to accommodate that. So there's going to be climate change. There are going to be other catchment-specific changes which we can anticipate. Like we know there's going to be some more dam construction. Or we guess that land use is going to change, maybe because of climate change. So we can construct scenarios and think about what might happen. And on that basis, we can answer these questions. To what extent can the current interventions within the reach be altered? You know, what latitude have we got for ripping out bank protection and so on? And what is the river likely to do if we do that? First question. Second question, to what extent can we actually intervene in the broader scale processes? Is there a better way of operating the reservoir, for example, that will reinstate flows that will help the river to recover under its own steam? And how may processes change in the near future, and what are their consequences? And that gives you a very good set of answers that enable you to then think about, can we just leave the river alone and it'll sort itself out? Or what can we do? How far can we go to reinstate this reach so that it can respond in the future under its own steam and in a sustainable way? And how far can't we because of human pressures? So we're realistic about long-term management or no management. Okay, so very, very quickly, an example. So this is the River Frome in southern England. This is a very low energy groundwater fed system. I mean, the low gradient, groundwater makes up about 70% of the flow. It's a rural catchment under a lot of agriculture because it's gently undulating land. We've defined 3 landscape units, we've defined 6 segments, and we've defined 17 reaches in the way I've already described. But the key thing here in defining reaches is a human impact, which is that there are large weirs all over the place in this catchment, but there are some particularly significant ones which define the ends of reaches, because they're interrupting all the processes. If we then apply this channel typology, we find we've got 3 basic types of channel in this catchment. That's all out of the 22. We've got low sinuosity single thread. We've got higher sinuosity, i.e. meandering single thread, and we've got anabranching. They've all got some combination of gravel sand bed. They're all unconfined, okay? So those are the basic types we've got. And if we conduct an assessment at the reach scale, the historical assessment becomes very important here. In that if you look at the old maps we've got, so we've got a map for 1889, we've got one for 1960 or 75, depending upon which reach we look at, and we've got a map for 2013. And these maps are all created by the same agency using the same conventions. They have a very specific way of mapping channels. So we have some confidence that we're comparing like with like. And on the right here is the sort of key take-home message, which is in this very low energy system, there have been changes, particularly in sinuosity and in channel width. And there have been some really consistent changes since the 1960 map and the present, in that virtually every reach has shown an increase in sinuosity and a reduction in width. Okay? If we look at our within reach features and we do these broad assessments of function, and again this is just the final take-home message, is that the hydromorphological function of these reaches on a very poor to very good scale is sort of intermediate and in some cases good. There is some sort of function there. We can say sum for the channel and floodplain features that you would expect to see. So we haven't got the complete set, but there's some indication that features are being produced and destroyed and there's turnover. Artificiality assessment is again middling, it's moderate. And the reason for that is there's a lot of interruption of longitudinal continuity due to these structures in the channel. But there's no interruption to lateral continuity. If the river wants to flood, it can. So that gives us that intermediate assessment. And the potential for the channel to adjust here, if it wants to, is again intermediate, in that the process dynamics are being interfered with, but there is space if processes get to a level where they can cause adjustment for adjustment to occur. Then we get to the interesting stuff. If you actually start to look in detail at any of these reaches, some very interesting things come out. This is the most active reach on the River Frome here. And in a very short period of time, between 2002 and 2008, we've had increased sinuosity and narrowing. It's very, very clear. Now, clearly, you know, this can change through time and get expansion, contraction. But that long-term trend is repeated in the short term here. And if you look at the Google Earth images, it's all to do with aquatic vegetation, which is why my view on that last site we went to yesterday is, if possible, leave it alone. So these pictures are taken in the early growth stage of the emergent plants so that you can actually see something other than plants. And what you can see at the top there, the solid black lines are the outer edge of the channel on the 1889 map. Okay? And then, so we can see this contraction. We can see there's virtually no riparian zone apart from what the river has built inside its own channel. It's agriculture beyond that. We see the occasional riparian tree sort of dotted along the riverbank. So the river's essentially unshaded in most reaches, therefore the aquatic vegetation just goes mad. I mean, loads of it. And certainly ranunculus is not endangered on the River Frome. It fills the channel in the middle of the summer. But the key plant is this Sparganium erectum, this really beefy plant. It grows within the channel, it traps fine sediment, it stabilises it and it degrades, and you get these series of geomorphic features. You can see them there. On D there, you can see this is when it's just starting to sprout. We've got this feature within the channel. We've actually got bank erosion on the opposite bank there. This is pushing erosion. Okay, so we have very little riparian zone, very few riparian trees, therefore lots of aquatic vegetation, and the channel is shrinking and becoming more sinuous as a result of being pushed by vegetation. If we look at the catchment, what we find, top graph, there's been a shift from pasture to cultivation, particularly switching around the Second World War. We've got a change in crop production, different crops, very intensively cultivated now. We've also got a shift in animals from sheep to cows and pigs. This all tells us there's more sediment, more erosion, more sediment coming off this land. No riparian zone to trap it. Where's it going? Into the channel. When it gets into the channel, it's then being trapped by the riparian vegetation, and it's being pushed back into the banks, into this narrowing channel. If we go back 100 years, there's no change in river type, but there is a change in river size. If we go back even further hundreds of years, the floodplain's been messed about one way and another through drainage and so on by human beings. And we suspect that there were different river types if you go far enough back. But we've got no direct evidence of that. Okay, so we can look at scenarios, warming climate, increased rainfall intensity, but also we could remove some structures. We could persuade the farmers to conduct agriculture in a different way, but that's unlikely. But what we could do is have a relaxation of riparian and aquatic vegetation management and let the river sort itself out. And in terms of our recommendations, and in fact what's actually happening in that catchment, the riparian zone is being replanted and reinstated. And what that will do, and we've got some pictures of what we think the river might have looked like in the past, what it might have looked like 100 years ago, what it's starting to look like now, and what it might look like in the future as you increase shade from the riparian vegetation, as you trap sediments because you've got a riparian zone, and as you still have aquatic vegetation but it's more patchy within the channel, what might happen. And that's it, that's the case study. And you can see if you go to the deliverables on the website, part 1 is really the only one you need to look at seriously. But part 3 is very useful because there are full applications of this framework to different rivers across Europe. So there is the Froome there, but there's the Magra, there's other, different rivers of different energy. And as I say, there's this aquatic sciences special issue coming up sometime soon. Thank you.